Bom dia, good morning. So it's a pleasure to welcome you all for this meeting in honor of Fernando's 30th birthday. I have to say one thing that I'm not responsible for this. So I think that the ones that are responsible for this meeting happening are Fernando's students. I hesitated a lot to accept to organize these meetings, but Sebastian was very insistent and managed to convince me otherwise. Matias, Ariel, Federico, they all played a key role for this meeting to happen. And I'm also very glad that Alicia accepted to join us in this endeavor of organizing this meeting to my good friend, colleague, and collaborator, Fernando. So without further ado, let me introduce the first speaker, César, one of César Massri, one of Fernando's students, who will talk about deformation theory of exterior ideals or something like that. Okay, please, César.
Hello, can you hear me? Yeah, okay. Okay, first of all, I want to thank the organizers and also Fernando. I want to congratulate for your 70th birthday. Today's talk is about deformation of exterior differential systems. It's a joint work with Fernando. First, a motivation why one wants to study exterior differential ideals or systems. One way to define a foliation is by vector fields with an integrable distribution. Another way is with forms, one forms. And you ask that a subshift of the omega 1 to be integrable. That idea can be formalized by saying that it is a differential ideal. So what is a differential ideal? First, we work with the exterior algebra. Let's say X smooth. Projective over C. Exterior algebra. It's basically the RAM complex. It has a differential. It is graded. The differential satisfies Leibniz, graded Leibniz. And a differential ideal differential is basically an ideal of this algebra, a sheaf of ideals on this algebra. It is graded and closed under the derivative. You can work the definitions of foliations with differential ideals. Also, partial differential equations are a particular case of differential ideals. But The motivation for us is that it is an ideal. It's an algebraic object. We have the theory of Hilbert schemes, abstract Hilbert schemes, in that algebra. So we have the theory of deformations of ideals. Moduli space of ideals is a Hilbert scheme. So let's talk about that. First of all, our category is the category of differential graded modules. What is a differential graded module over this algebra? Where it is a complex, a sheaf, a graded sheaf. Each component is OX linear, OX module, could be coherent. And we have an action of a graded action of the algebra. F has a differential of degree 1. And morphisms between two of these objects are graded, OX linear, and commutes with the differential. So we have the space of the sheaf, abelian sheaf of maps between two of these objects. We denote it like this. It is not OX linear. It is not an OX module. Also in this category, we have the notion of internal OM, that is a graded object with a differential, and we have a tensor product adjoint of that internal OM. Okay. Second point is differential ideals. A Pfaff ideal. What is a Pfaff ideal? The idea is to formalize the notion of a foliation in this setting. Okay? So first definition. Pfaff ideal. Basically, it's a differential ideal generated in degree 1. E is Pfaff if it is that is EK K minus 1 plus it has to be closed under differentiation, so it's D of EY plus omega. So a Pfaff ideal is generated by one forms. Now we want to define the notion of integrable Pfaff ideal. And definition, E is integrable Pfaff.
It's a wedge of theirs. Instead of a sum, it's a wedge, right?
Yeah. Integrable Pfaff if DDE1, I1, lives in I1 wedge omega 1. This is the way that once define the way in which we can define foliations as a subshift I1 inside omega 1, satisfying this integrability condition. The problem with this is that, in general, this hypothesis is not valid in the whole variety. So we have to define the notion of singular integrable Pfaff ideal. Is singular. Is basically if there exists an open subset Zariski open such that the ideal restricted to U is integrable Pfaff. Okay? In a moment, I will give examples. The final definition that I want to say is a saturated singular integrable Pfaff ideal. The notion of saturation that also appears with distributions and foliations. How can a saturated singular integrable Pfaff is a bar, which is the double dual of a singular integrable Pfaff ideal. A singular integrable Pfaff ideal. Why we are taking the double dual? This is because we want that the shift to be reflexive. In other words, that the quotient be torsion-free. For example, this one, we want to be torsion-free. We eliminate when we.
No, if it's principal, it does not kill.
Okay. We want that this to have a def 2 when we take the double dual. Okay, so let's make, for example, a proposition here. Three. For example, if E1 is generated freely on U by omega 1, omega q. Assume that in some open subsets, these forms are linearly independent. Then, if one take the ideal generated by these forms and one take the double dual, then this ideal, the saturated, is given by etas so basically it's the kernel of multiplication by omega. For example, also if we have more than Q, by omega 1, then E bar is similar So in a way, the notion of saturated singular integrable Pfaff ideal gives us the standard notion of foliation given by forms. We need to add a lot more of forms. So this is the second point. Now, what about the formations of these differential ideals in general? The formations. So the theory of the formations of ideals, standard ideals, is the Hilbert scheme, right? And there's the theory of the formation of ideals in an algebra. It's called abstract Hilbert scheme. And there's an article from Artin where he developed this theory. We also did the same calculations, but I prefer to cite Artin. So what's the idea? First of all, what is a family of differential ideals? Well, it's a pair, a map. And an ideal such that this is flat over S. Then one can define the formation factor or the Hilbert scheme. Which are quotients of omega x. The points here are pairs such that Q is a quotient of where we identify two quotients if there exists something like this. Basically, the equivalence class of these objects are ideals. So this is a subfunctor of the quote functor. Then we use the notation. We say EI.
So F is a GJ module.
F, yeah. I in Hilb. This represents, in fact, the quotient omega over I. So we have a scheme, Hilb omega. We know the tangent space of I and the obstruction theory from the general theory. Let's say if, well, the tangent obstruction theory of is given by this space is the tangent space, and this space is the abstraction space. This is very difficult to compute, but if it is 0, it implies that this point is smooth. And this is also very difficult to compute, but it's the tangent space. For example, in the case of a saturated singular integrable Pfaff ideal, if E is a saturated singular Pfaff generated omega in Pn, for example, then this space is easy to compute and gives etas such that so the tangent space of this differential ideal is the same as omega in the space of integrable one forms. A similar computation can be done for saturated single integral Pfaff ideal generated by several one forms. It gives a formula like this.
Is there no difference between the saturated case and the non-saturated case? Because all these definitions you're giving, they work on the Hilbert scheme, the full scheme usually, right? But
Yeah.
then since you're on an open set, right?
Yeah.
So I would say that all deformations just stay saturated, right?
In this case, yes, locally. If the ideal is saturated, locally they are all saturated. But in general, no. In general, if in case of a general differential ideal, anything can happen. This extends the ideals in general, the standard ideals, because you can take, for example, as you take E0, an ideal. This lives in OX, so it's an ideal in. You can take the generated by, for example, one equation, and you take the differential ideal generated by this. This represents the hypersurface H. So this theory extends that that case. But in case of saturated, we have the same moduli space. Okay, so what's time? Have 20 more minutes? Yeah.
25.
Yeah, okay. Okay. Now let's talk about the theorem, our theorem. Five, four. So the idea of the theorem is to give a stability theorem about the sum of differential ideals. We want to say that if we know each, well, let us write. First, I want to give a lemma that is easy to lemma, WM. Okay, let X reduce irreducible scheme F map X and X and F, and assume that the differential X going that this map is surjective. Then the image of F is a component of Y. Irreducible component of Y. Irreducible. Let us prove this. These are going to be our main tool in the theorem. So first, the first remark is that given that X is reduced, F must, the image of F is also reduced. So F factorized through the reducible F factorized ICES through E-red. So we have X. This is F. This is because X is reduced. This implies that Y is reduced. Y in Y. And what about the differential? If we take differential X, Tx, X inside T, Y red, Y. Given that this map is surjective, the image must be must be equal. So the dimension of the image must be equal to the dimension of the component where E lives. So this is a component. That's okay? Okay. The idea is to choose Q irreducible reduced sets of the Hilbert scheme. Reduced, irreducible, and we take the product. Define mu. Mu is the sum of ideals. Here we take E1, EQ, and we take the sum. The question is when this image is an irreducible component of the Hilbert scheme. For example, this could be logarithmic foliations, and we take the sum of Q logarithmic foliations. So what are the hypotheses? Reducible. Bueno, assume that this natural map this is the quotient map. Assume that this map is surjective for all j. Pj is the projection. And we are assuming that this map is surjective for all q. Why?
What is I?
I. Here I is a generic point of
On the other side.
the sum. I didn't say that. Where Ej, Fj generic. And we take the sum. Here there are a lot of technicalities, but for example, here we are putting a rational map. Okay. The idea of the theorem is to prove that this hypothesis implies that the differential is surjective, and then the image of mu will be a component of Hilbert. Okay? Sum surjective. So the idea of the proof is the following. First, we compute the derivative of mu explicitly, and the second part is to prove that with this hypothesis, that differential is surjective.
What's the conclusion of the theorem?
I didn't say that. Then d mu is surjective at okay. Proof. This is fab. Okay, the proof, it's easy to, okay, first, the differential of mu at a point E1, EQ goes from the tangent space of this to the tangent space of this, which is some, that's ij where I is the image of mu. So the differential of mu takes Q deformations, which is morphisms, and gives a deformation of I, which is another morphism here. This can be made explicitly. Phi1, Phi2 are elements here. In some element of I, which is a sum and one can show that this is equal to sum. First, we apply the deformation to each omega, and then we project. This is well defined. If we choose another expression for this omega, it gives the same expression, so it is well defined. And this is the expression of the derivative of mu. With this, this implies that we have a commutative diagram that I'm going to write here. E, J, omega mod I. No. Here. Yes. So we have this map S, which is the sum, which gives a morphism here, like this, applying the here. No, EJ. Applying this functor on with respect to omega modulo I. Then we have these maps, which are the sum of this. And the differential goes from here to here, and this formula says that this commutes. This implies that given that S is injective and this is surjective by the hypothesis, d mu must be surjective. So assuming that these maps are surjective, we can deduce that the differential must be surjective. And with that, we can use the lemma to prove that the image of mu must be an irreducible and reducible component. With a little more of work, one can compute the dimension of the image using the dimension of these spaces. And 10 minutes to finish this. So we reduce the problem to this kind of hypothesis, a map to be surjective. This map sits in a long exact sequence. If we take this short exact sequence and apply the functor, we get this EJ omega EJ this is PJ EJ we have an X1 So the surjectivity of this map is equivalent to the injectivity of this map, because this is a long exact sequence. So one way to guarantee that this is surjective is by requiring that this is 0, for example. Because this map would be injective. Now, this map is difficult to compute, but it appears in a spectral sequence, in a 5-term exact sequence. And here we have two maps, this H0X. If these two maps are 0, this implies that this is 0, and this implies that Pj is surjective. Because X1 appears in the middle of a 5-term exact sequence, and the 2 in both sides is this and this. This comes from the Grothendieck spectral sequence, taking global sections and the shift ohm. If you take those, that composition, it gives you this in the middle and this in the sides. So if these two are 0, this implies that this is 0 and this is surjective. And this implies that d mu is surjective. So several of the work that we were doing was trying to figure out when these two spaces are 0. This space of the shift X, we managed to prove that under conditions like def2 and stuff like that, we can say that this is 0 under good hypothesis. The problem came with this space. This is okay. No, this is here 0 and this is 1. With this space. That we, yes, the idea is to prove that, for example, in the logarithmic foliations, this is 0 or not, and that kind of things. So, okay, I think that I stop here.